All right, 6.3 logistic growth. Last section in Unit 6. This is the last section before your final for the semester. Should be the last one in the semester 1. Okay, logistic growth is a Calculus 2 kind of content section, whatever anyone you call it. This probably will be on your AP exam. This is a pretty good chance of being on there. So please make sure, I guess, you're going through and making sure we understand this. We did exponential growth and decay last section. We're going to do logistic growth now. In exponential growth, okay, we can assume that the rate of increase or decrease of a population anytime t is directly proportional. Okay, we talked about that as well. In other words, the dp over dt is equal to k times p. The k is some constant, right? However, in many situations, population growth levels off and approaches a limited number L. We call this number L the carrying capacity. Okay, and if we can understand that it remembers the carrying capacity, that is going to be a huge piece of what this kind of problem is. If we can get into that form that we'll talk about here in a little bit with carrying capacity, this is going to be an easy question, honestly. It's really not a hard question, but you got to understand some things. Because of limited resources, meaning like China's population, okay, is 1 billion plus, and India is approaching China's population, going to exceed it, but there's going to be some point in time where the amount of resources in China or in India are going to be limited because of the amount of people, right? And therefore, the amount of people growing can't grow as much every year, so there's going to be a certain limit as to how much people can actually live in that country. Or in decrease, okay? It depends, but they're proportional both to P and to L minus P. All right, and now this is what we call logistic growth. So this is the differential equation here. dP over dt is equal to K times P times L minus P. All right, so the L, right, is our carrying capacity. That's going to be important. If we can find the second derivative of dP over dt, we can find out when P is growing the fastest. Okay, so this was the example here, or these three examples are pretty similar, but this is really as they're going to look like. Like there's not going to be any much difference in any of these questions. Okay, but you got to understand kind of some basic things. So the population P of T of fish in a lake satisfies the logistic differential equation dP over dt equals 3P minus P squared over 6,000, where T is measured in years and P of 0 is equal to 4,000. So what is the first thing we got to do? Well, we have this equation here. The first thing we got to get it to do is to look in this form. So dP over dt is equal to K times P times L minus P. Okay? So what I want to do is it's K minus P, and this is a P squared, right? So I'm going to take out a P because there's P's in both. Okay? Then I'm going to take out some constants. So I want P by itself. So in order to get P by itself here, all right, I need to take out the negative, I'm sorry, not a negative, the 1 over 6,000. I need to take out the 6,000 that's in my denominator. So if I take out a P over 6,000, I'm left with, okay, in order to get this to be 3 when I distribute it back, this is now got to be 18,000 minus P. If I were to redistribute, I get what I started with, okay? And me getting what I started with is going to help me in every single thing on this page here, okay, on this question. This here is a legit question, part A. This is one of them that could be on your AP exam. Well, this whole thing could be, but really part A is like 1 point, all right? And when it says the limit of P of T as T approaches infinity, well, P of T is basically what's going on here, right? If I were to think about this, what am I actually looking for? Well, as this function approaches infinity, this is what we want to get to, what's called a carrying capacity. So what is the amount, or the highest amount of the population of fish that this lake would actually work with? Like, there's no more that could probably fit in this lake because of all the other resources, right? The food, or maybe the other fish are dying off so they can't have as many fish in there, or something like that. So the carrying capacity is the the L value. Sorry, I had to find make sure I had the right letter. Is the L value. And this L value right here is actually 18,000. So 18,000 is our answer. This is the highest amount in this example. This is the most amount of fish that could be in this lake. So then, what's the range of the solution curve? Well, if the initial right here at year 0 is 4,000, then it goes from 4,000 to P, which then goes to 18,000. Sorry, 18,000. So it could go from 4,000 to 18,000. It can't go more than 18,000 because that is the carrying capacity. It will not allow for any more than 18,000. Okay? All right. Those are pretty simple, okay? You just got to make sure it's in this format. And once you're in this format, it tells you a whole bunch. For what values of P is the solution curve increasing, decreasing, and then justify your answer? So how do I find out if the solution curve is increasing? Well, remember, increasing, decreasing deals with their derivative. So I got to find out when the derivative is equal to 0. So I'm going to take 1 over 6,000 P times 18,000 minus P, set that equal to 0. And how do I do that? Well, this right here is equal to 0, okay, if I think about this. And this here is equal to 18,000. All right, so those are my two critical values. Those are my two critical points. So I'm going to make a little table. So P could be 0, could be 18,000. I'm going to skip a spot there. I'll tell you why. Or it could be, well, it can't be any bigger, right? Because it doesn't really, like 18,000 is our carrying capacity. Okay. But, let's see here. I'm going to pick like a 9,000 in here. The reason I picked 9,000 is because like it's going to be nice to kind of divide and do some stuff when I plug in. If I pick like 3 or 1, I guess I could pick 1 and maybe that would work too. But really you want to pick a number between 0 and 18,000, right? Just like we normally do on all of our stuff. So the dp dt, this is our slope. At 0, we get 0, right? At 18,000, we get 0. At 9,000, if I plug it in, I'm gonna get a positive value, and if I plug in 20,000 or anything bigger than that, I'm gonna get a negative value. Okay. So what's going on? Well, the solution curve is increasing. Okay, the solution curve is increasing from 0 to 18,000. So from 0 to 18,000, the solution curve is increasing. From 18,000 to infinity, the solution curve is decreasing. Because that's what it says, right? So 18,000 is the highest point, all right? And then when it goes past 18,000, it's not going to increase anymore. It's going to like kind of stay, it might be close to 18,000, but it's not going to be exactly 18,000. It might get a little bit less based on how many more fish are there, right? Okay, for values of P, which is the solution curve, concave up, concave down, and justify. Well, concavity deals with the second derivative. So I'm going to find the second derivative. So dp over dt is equal to, now in this case, I'm going to come back to the original, okay? So I'm going to come back to 3p minus p squared over 6,000. I'm not going to use the one that I kind of manipulated to get my kp times L minus p. I'm going to come back to the original because that's going to really just make it easier, right? So dp over dt is equal to that. And so d squared p over dt squared is equal to 3 times p prime minus what? 2p p prime over 6,000. Okay? Hopefully we can remember how to do implicit differentiation. Therefore, the second derivative is equal to d squared p over dt squared equals, I got to plug in, remember, p prime, which is right here. I got to plug p prime in, okay? So I get 3 times 3p minus p squared over 6,000 minus 2p times 3p minus p squared over 6,000, and all of this is over another 6,000. Holy cow, that's some crazy stuff going on there. I could have done it probably a little easier, but that'll work. I could have factored out a p prime, and maybe actually probably would have been easier actually. Factored out a p prime. Yeah, let's do it that way. Let me back up a little bit and do it that way because this is crazy. So if I take this, I'm going to factor out a p prime. Okay, I'm going to end up with 3 minus 2p over 6,000, which is really p over 3,000, right? P over 3,000. Oops. Let me go back. Let me go there. Okay. So p prime times 3 minus p over 3,000. All right. So now plug in p prime, okay, which is that. So I'm going to end up with 3p minus p squared over 6,000 times 3 minus p over 3,000. Great. That actually works out a whole bunch. That works out a lot better. A lot better. Okay? And you can even clean it up more if you really want to. You can really clean it up. That's probably okay, though, honestly. That's probably okay. So where does concavity actually, like, happen? Where does it change? Well, it means that when the second derivative is equal to 0. Okay, so when that second derivative is equal to 0, you can go ahead and solve these. Okay, I'm just going to write down the answer. So p is equal to 9,000, comma, 0, comma, 18,000. Those are the three values at which your concavity is going to change. Okay, or potentially change, right? Those are critical values that could potentially lead to a changing of concavity. Okay, if I make a table, and I'm going to use 0, I'm going to put 9k just because of space. Actually, let me do some awesome stuff here. I don't want to scroll down because I'm going to lose all this other stuff. So I'm just going to kind of make it over here. I'll make the table over here. Okay, so I got p, make a table. I got 0. I'm going to put value of 5,000 because that's in between 0 and 9,000. Okay, I'm going to put 12,000 because that's in between 9 and 18,000. And then I'm going to put 20,000. Just like I did before. All right? And this is d squared p over dt squared. At 0, we know it's 0. If I plug it into the second derivative, I'm going to get 0. Okay, if I plug it in, you can definitely see that you're going to get 0 times 3, which is still 0. If I plug in 5,000 and I do that work, you get a positive. So it's concave up. If you plug in 9,000, you get 0. If you plug in 12,000, you get negative. If you plug in 18,000, you get 0. And if you plug in 20,000, you get a positive. Okay, concave up. So we're going to use this information, all right, to then answer part E, which is, let's see here, part E, okay, is inflection points. So do I have an inflection point? Yes. So you have an inflection point. So yes, you have an inflection point. Oh, well, I guess I'm sorry. We didn't finish answering part D. So we put the table, but we didn't actually answer the question. So concave up when it's from 0 to 9,000, union 18,000 to infinity. Concave down at 9,000 to 18,000. And then that's it, right? There's no other one. Okay. Oops. 18,000. Okay. So there we go. Concave up, concave down. Does the solution curve have an inflection point? Sure. Yes, there's going to be one. Yes. At p equals 9,000. Okay, because concavity changes. Concavity changes. Okay, now you might be like, well, concavity changes at 18,000, and thus I'm going to get yes, technically, if you want to say that, that's true, but because 18,000 is the highest value that's our carrying capacity, right? Anything after 18,000 really doesn't matter too much anymore. So it basically is a moot point. Okay, so anything between anything in the middle of our solution curve, right? So our solution curve, remember from part B at the top, was only between 4,000 to 18,000. Anything above 18,000 doesn't actually fit in my solution curve, so it doesn't matter. Okay, so now I want to use that information to sketch the graph of our function. So here's what I'm going to do. I am going to draw a graph. All right, I'm going to make so it's a couple things. One, it said p of 0 is equal to 4,000. That was in the problem. So that means some value that's at 4,000. That's 4,000. Okay, when x is 0, see when t is 0, really, you get 4,000. What happens? Well, we know a concavity changes at 9,000, so I'm going to make a dot here at 9,000. And then figure up here is 18,000. What happens at 18,000? Well, this is our carrying capacity. So our carrying capacity is going to be like a dotted line all the way through infinity. This is the highest that function in terms of fish can go. So what I'm going to do is I'm going to start off at 4,000. Remember, from 4,000 to 9,000, it's concave up. So I'm going to make it concave up. I'm going to kind of come to 9,000, and now the function is now going to be concave down to infinity. Okay? And so right there is my inflection point. And so this is concave up, concave down. You met all the requirements. That problem is done. This problem is not a hard problem, but you got to make sure we get it in that form first. Kp times L minus P. Kp times L minus P. If we can get it in this form, right, dP over dt, then we are going to be all set because everything stems from there. All right, let's go to example 2. And then it's very similar again, but we got to make sure we understand the process. So here we go. Population of fish satisfies that logistic equation, and it's the same one, where t is measured in years and p of 0 is equal to 10,000. Okay, well, what do we know? Well, let's see if we can get this in the form of Kp times L minus P. So I got dP over dt equals, I got to take out a P. I'm going to take out a 6,000 again, because this needs to be a single P, times 18,000 minus P. All right, and that's what I want. I got a good thing. So now let's use that information. Carrying capacity, that's what part A is always going to be. Limit as it approaches infinity. Our carrying capacity is going to be 18,000. That's a piece of cake. What's the range of the solution curve? Well, if its initial is 10,000 and I can't go past 18,000, well, that's my solution curve. That's the range. So 10,000 is less than or equal to P, which is less than or equal to 18,000. Okay. Next one, when's the solution curve increasing? So this is when the derivative dp dt is equal to 0. So if I set this equal to 0, I'm going to get p to be 0, and I'm going to get p to be 18,000. So now, again, you fill in your table. Okay, so I got 0. I'm going to use, what number did I use this time? Oh, it doesn't really matter, I guess. So we can use 18,000 would be, actually, no, we don't want to use any of that stuff, do we? 0 is not in anything, so that doesn't even matter, okay? The only ones we care about are 10,000 in between 18,000. So we can probably, hopefully, see that this is going to be increasing. So if you wanted to make your table, well, let's plug in 0, might as well, it doesn't really matter. And then I'm going to choose like 12,000, okay, and then 18,000. If I plug that in, this is going to be 0, this is going to be 0, and this is going to be plus. Okay? And so technically, if you want to think about it, from 0 to 18,000 is, increasing, but we don't really care about that right here. We're talking about 10,000. So we can say 10,000 to 18,000 is going to be increasing. All right? And I think if I actually went back to the first problem, I think I made a mistake with what you guys wrote down. So here, increasing as well, okay? Increasing is from 4,000, okay? It's not 0. Remember, I think I said increasing. If I look at my notes here, I said increasing from 0 to 18,000. All right, it's not from 0 to 18,000. it is only from 4,000 to 18,000. Okay, increasing from 4,000 to 18,000. All right, because remember our graph, okay, this is 4,000, this is 18,000 here, and it goes up like this. Okay, so it's increasing up until that value. All right, and again, 0 doesn't work because our solution curve, remember, was 4,000 to 18,000. Okay, so sorry about that. Hopefully we fixed it in our notes. Okay, so let's move on. All right, let's see what we can do here. Okay, so we get increasing, fantastic, from 10,000 to 18,000. We can see that it's plus. We're good to go. It is not decreasing at all. Okay, this function does not decrease from 0 to 18,000 or from really 10,000 to 18,000. For what values of p is the solution curve concave up? So that's when the second derivative is equal to 0. Okay, I got to find this double derivative. I'm going to skip a lot of steps. You guys can find the double derivative, but I'm going to tell you what it is so you can see what it is. So d squared p over dt squared, which is our double derivative, is equal to, I factored out a whole bunch of stuff here. Okay, well, let's just do it this way. So it's equal to p prime times 3 minus p over 3,000. So it's actually, it's the same function, right? So, I mean, it's the same function, so you should get the same answer. Okay, so p prime, we know is p over 6,000. Let's just, I guess, put it original. 3p minus p squared over 6,000 times 3 minus p over 3,000. Set that equal to 0. You are going to get p is equal to 9,000, 0, and 18,000, just like in the last problem, because it's the same function. Dun, dun, dun. Okay, so now what? Well, if we actually do the chart there, okay, we can actually come back to my previous chart. Let me see if I can come back to it. We can come back to my previous chart, which is right here. All right, at 9,000, it's 0. So at 12,000, it's negative. So in between 9,000 and 18,000, it's negative. So that means it's concave down. Right. So now let's go back and look at this one here. So that means it's going to be concave down from 10,000 to 18,000. Okay, concave down from 10,000 to 18,000. Does the solution curve have an inflection point? Well, no, because 9,000 isn't even in our like solution curve, right? 0 is not in our solution curve, so those actually aren't solutions. 18,000 is at the far end. That's the biggest there is. And so there's no other critical value that changes signs. So we have none. So no inflection point, none inflection point, because d squared p over dt squared does not change signs. Okay, fantastic. Let's go to the solution curve. What the heck does that thing look like? I'm just going to keep scrolling. I don't even know what I'm doing right now. I'm just kidding. Okay, sketch it. So what do we know? We know that the initial value is 10,000. The carrying capacity is 18,000, so there's my line. So 18,000, okay? The function is increasing from 10,000 to 18,000, but it's concave down. So just like that. And that's what my graph looks like. Okay? All right, let's do the last one here. Let's call it a day here in a little bit. Hopefully this one goes faster. Oh man, it probably doesn't. So it's the same differential equation, but now my initial is going to be 20,000. Okay? So again, the carrying capacity, right? Let's actually factor this out. We might as well do it. Okay? dp over dt is equal to p over 6,000 times p minus p is out, yeah. P over 6,000 times 18,000 minus p. So again, carrying capacity. That is what the function is doing at infinity, 18,000. That's the biggest it could be. Okay? What about the range of the solution curve? Well, if we know the carrying capacity is 18,000 and the initial is 20,000, that means that it's going to be, in this case, it's going to be a little different, but it's going to be 18,000 to 20,000. So our graph is going to have your carrying capacity and our function is going to be above it, starting above and coming down. Whoa, that's crazy. What values of p is the solution curve increasing? Again, if I look back at my example type 1, okay, we can see, let's scroll all the way back here because I can. We can see that it's after 18,000, it's actually negative. Okay, it's negative. So let's no, that's not what I wanted. Right there. Okay, so we can say that it's decreasing from 18,000 to 20,000. Because that's all I care about, right? That's in the solution curve. Anything outside of those bounds don't matter. Don't matter. I don't think that works as a English vocabulary, but that's okay. So remember, this was when dp over dt is equal to 0. This one here is concavity and talks about d squared p over dt squared. It's double derivatives when that equals to 0. That is concave up. Concave up. Up. When 18,000 to 20,000. Okay, 18,000 to 20,000. Okay, now what? Well, does it have an inflection point? So anything after 18,000 was always decreasing. So because there's no critical points there, like, it doesn't have an inflection point, right? The concavity does not change. So no, because the double derivative doesn't change signs. Does not change signs. Okay, well, what about the sketch now? Well, if my carrying capacity is 18,000, which is that line, that dotted line there, but my initial is 20,000, which is up there, and it's concave up, but it's decreasing all the way, so it's going to look like that, all the way to infinity. All right, that's it, man. Logistic growth's not terrible, but you got to understand. Please make sure you're writing your equation of dp over dt of whatever you got there as k times p times L minus p. And once you got that, the L is your carrying capacity, and you use that information for a lot of stuff. Okay, a lot of stuff. So it's not a hard thing. This could be on your AP exam. It's a pretty good chance it will be. So I will see you next section, or next unit, in unit 7, which is going to start some crazy volume and area between curves and some awesome stuff. So deuces, I'll catch you on the next one.